Welcome, everyone. If you just joined, my name is Mark Tarina, and I'm the marketing manager for Geneva Pipe and Precast, a Northwest pipe company. Today's presentation focuses on common design challenges for precast structures, pulled directly from real questions and project examples our sales and engineering team have worked through with our customers, as well as topics raised by attendees from our previous webinars. Leading our discussion today is our Director of Engineering, Ashley Wilson. And assisting with Q&A is Geneva Sales Manager, Cody Mangum. So with that, I will turn it over to Ashley. Ashley, welcome.
Thanks, Mark. So yes, my name is Ashley Wilson Gregory, and I'm excited to be here with you all today. Let's see, I unofficially started with the precast industry in 2010 when I was a grad student doing concrete pipe research, and then officially joined the precast industry in 2012. I've been in various engineering and TRE roles since then, and I'm really excited to talk to you all about some of the things I have learned during that time. So today we are going to be discussing various topics related to precast design. It is a pretty packed hour, so I do plan on keeping most of the topics pretty high level in order to get through everything within the hour. I do want to encourage you to please ask questions in the Q&A section, and if there's anything you are interested in learning more about, please let us know in the survey at the end of the presentation. We will use that information to help us develop future webinar topics. Okay, so as I was looking through the registration list, we have people joining from all over the country. So I want to take a moment to introduce Geneva as well as the Northwest Pipe Companies. Geneva was established in 1956 and joined Northwest Pipe Company in 2020. We have 3 precast manufacturing plants located in Utah and provide a variety of concrete infrastructure products and custom precast solutions. Northwest Pipe Company is located all across the country, with corporate being in Vancouver, Washington. The pressure pipe plants are located in California, Texas, West Virginia, and Mexico. And then Park USA, which also produces precast concrete products, is located throughout Texas. Today, we are going to cover a variety of precast topics. These topics were chosen based on questions received and observations made from both our sales and engineering teams here at Geneva. First, we will discuss common precast design challenges, then resolving specifications and standard detail discrepancies, followed by reinforced concrete pipe classes, concrete pipe versus concrete box in terms of hydraulics, and the manhole sizing tool that we have built. There will be time at the end for a Q&A session. You don't have to wait till the end of your presentation to ask your questions. You are welcome to drop them in the Q&A portion of the webinar at any time throughout the next hour. All right, let's begin. So why is it important to leave a minimum amount of concrete above openings? Providing concrete above openings can help reduce cracking during shipping and handling, and also provide adequate structural integrity for the structure. Typically, we recommend about 6 inches above an opening. Why is it important to have a minimum amount of concrete in between openings? The answer here is for many of the same reasons as before. It is typically recommended to have anywhere from 6 to 12 inches between openings in the walls. Ultimately, we want to provide a proper structure which is built with structural integrity in mind. We will discuss some examples throughout this presentation on common issues we see and how we can all work together to achieve the best results. First, let's talk about openings in precast structures. Commonly, we will see structures that are undersized for the openings required. When this occurs, it can reduce or eliminate the beams above or between openings. By taking into account the chord diameter and not just the internal diameter, we can work together on sizing structures correctly and avoiding delays and issues in the projects. So, what's the difference between ID, OD, and your chord diameter? Well, The ID is the inside diameter of the pipeline and is normally the number commonly referred to as the pipe size. The OD is the internal diameter plus the wall thickness. And finally, the cord diameter is the extra space that we provide at the time of when we manufacture it at the plant. And this cord diameter is larger than the OD. The cord diameter is larger to accommodate for slight grade changes and properly installed pipe connections in the field. The cord hole sizes will be dependent on the manufacturer and their specific tooling, but in general, 1 to 3 inches on each side is pretty safe to assume. An example of this is shown here on the screen, where we have a 24-inch seawall pipe, which has an OD of 31.5 inches and a cord diameter of 36 inches. If you are only considering the 24-inch when you're choosing the precast structure size, there's a chance that the structure could just be too small or undersized for the application. Another common potential issue we sometimes run into is when the pipelines coming into the precast structure are on a skew. When you have a skewed pipe, the openings must be much larger depending on the angle of the pipe. As you can see from this figure, the width of the opening goes from the point where the pipe enters the outside of the wall through the point where the outside of the pipe enters the inside of the wall. The larger the pipe and the larger the angle, the larger the opening will need to be. Okay, so let's talk through an example. The plan view on the left shows two 24-inch pipelines coming into a 4-foot by 4-foot box. One pipeline is entering the south wall at 45 degrees, and the other 24-inch pipe is entering straight into the structure on the west wall. Due to the angle and size of the skewed pipe, in addition to accounting for a little bit of buffer with that cord opening, it is found that the 24-inch pipe on a 45-degree skew requires a 52-inch wide opening. This means we would have to cut or clip the corners, which is not recommended. Therefore, the structure would be considered too small, and we would need to upsize it to a larger structure. On occasion, we are able to skew the actual precast structure to better align with a skewed pipe. But in this instance, our only option would be to upsize due to the multiple pipelines and the skew. This change has a potential for RFIs during the submittal process and the potential for delaying the manufacturing time to the job site. Here's another common situation we see. A customer wants to use a stock knockout box, but the incoming pipe is too large for the knockout. Typically, the beam above the knockout, at least in Geneva's stock boxes, are roughly 11 to 12 inches thick, and that beam needs to stay intact in order to maintain the structural integrity of the box. In the example shown here, the standard 3-foot by 3-foot KO box called out is 3.5 feet high. When the hole required for a 24-inch concrete pipe is 30 inches based on the OD, the hole would encroach the upper beam and compromise the knockout box. However, we see customers do this all the time in an effort to save money or avoid longer lead times and costs of building a custom structure. Another way to look at this example is that the top of the pipe must be 2 feet below grade for this knockout to work. Some potential options or solutions could be to lower the pipe grade, use a taller stock KO box, maybe a 4-foot deep box, and also you could use a smaller pipe if that works in your project. Or if all else fails, we can build a custom box specific to what you need. Occasionally, from the manufacturing side, we run into situations where standard details and the specifications do not match up. So let's talk about a couple examples and talk through how we can plan ahead for some of these situations. Okay. So the first here that I want to talk about is when a project located in one city has specifications referring to a different city. When we see this, we see this more than you might think we do, and it can really flag some questions on our end. Ultimately, we want to make sure we produce the correct structure and ship the correct materials to your job site. And when we run into these scenarios, we don't necessarily know if it's a typo or if it's some sort of dual city requirement, or if there's a water network that's owned by someone else traveling through your project. We just don't really know. So an example here shown on the screen is a ringing cover for Surprise, Arizona that was specified in the plans. But the project is actually located in Sun City West, Arizona. They're neighboring cities, so maybe they have a joint project or waterway, or maybe it's just a typo. This can cause delays due to RFIs or potentially cause the incorrect ringing cover to be delivered to your job site if we don't catch it on our end. If you are someone who writes specifications for projects, please be sure to double check specification references are what you actually intend them to be. And if you really want to keep it simple, and if the municipality allows for it, remove the requirements for the city logos on ringing covers and just leave it as a plain storm and sewer. That makes it less chance of getting things mixed up. All right. Another example of standard details versus specification issues are when general manufacturing specs are used without being customized to the city specification. There are times where the two conflict one another, and we either have missing information or we have missing information, and then this poses more questions from us to you. In the picture, the dimension of the precast structures are left somewhat undefined. And to be honest, this happens pretty commonly specifically when a product manufacturer shows the connection of their pipe to a product or to a precast structure, but then leaves the elevation of installation up to the design engineer. Then the design engineer assumes that the manufacturer has already defined this, and thus leaving us without all the information we need. The best way to solve this is in the design phase of the project. As you are selecting different general manufacturing specs, double check that there aren't any to be determines needed. If there are, please provide that information somewhere within the plans near that general specification. That will help us properly size, as well as put the openings in the correct locations so there's no confusion or issues on the job site. Okay. Our last example here is shown on the screen. On this one, it's called out that cast in place or precast options would be acceptable. A couple of the issues that are present with this specific detail. First, there's really no room left for the structure lid on the drawing. And how we would build something in the precast manufacturing world would be to have that lid on top of your top piece. So there's no real room for that lid. Next, the structure is drawn assuming a flush or embedded ringing covers, which is not how they are typically produced. Typically, they're set a little bit higher than the structure. It also does not account for any grade adjustments or use of grade rings, meaning that this structure would have to be installed exactly to the finished elevation, which can be a challenge on the contractor's side. Even if it is placed exactly where it needs to be at the time of installation, this could also pose some issues if the roadway ever needs to get repaved or refinished at a later time. These are just a few examples of the situations we see. If you are ever in doubt, please call us. We have a team of sales professionals that can help figure out the correct structure for your specific situation. Okay, so reinforced concrete pipe standard classes. What are they and how do we specify them? We do receive a lot of questions regarding reinforced concrete pipe, specifically related to the pipe classes and how designers can choose the correct pipe class when developing their plan sets. So I do want to spend a good amount of time talking through some of the pipe design and different classes, as well as some resources that are available for free that everyone has access to help them within this process. Okay, so what functions must an underground pipe perform? It must be a conduit, allowing water to move from one end to the other. And it must be a structure, providing support for whatever is being placed above it. A buried pipeline works as a structural system when it incorporates the properties of what two things? First, it must be the pipe and the soil around it. These two materials work together to create a complete structural system. Now, not all pipes are created equal. Specifically, there are rigid pipe systems and flexible pipe systems. And a great benefit of concrete pipe is that it is considered a rigid pipe system. With that, it's safe to assume that the physical concrete pipe will take on anywhere from about 70 to 90% of the load coming down through the roadway above. And then the soil surrounding the pipe will take about 10 to 30% of that load. A rigid pipe is designed to resist stress and transmit the loads on the pipe through the pipe walls to the foundation soil beneath. Here we can see the basics of an RCP trench. Starting with your foundation at the bottom, next you would loosely place bedding under the middle third of the pipe. The bedding should then be placed up to the spring line or that middle of the pipe. It is in the bedding area, so this area here, that the soil support is important for the structural aspects of the pipe. Assuming the load travels down the pipe walls, from up here, it travels down and then down through the pipe walls. Once it's past the spring line, the pipe would start transferring the load into the soil below. Above the spring line is not considered a structural component for the pipe, but more so for whatever is being placed above the pipeline. There are 4 standard installations that are described in ASTM C1479, type 1 through type 4. Having an understanding of these installations will be very beneficial for the overall success of your projects. In this table, the soil type and compaction required for each installation type is described. Type 1 is considered the best installation and requires a 95% compaction rate of category 1 soil up to the spring line of the pipe. Conversely, type 4 requires no compaction when you use category 1 and 2 soils, or 85% compaction for category 3 soils. So you can see they're quite different between types 1 and type 4. Type 1 is considered the best installation and honestly very hard to achieve on the job site. It is also the most expensive to build. Type 1 relies on the pipe the least out of all the other options because it relies so heavily on the soil surrounding the pipe. As the installation number increases, the more the pipe is utilized in the strength throughout the entire system. So a couple slides ago, when I said that the pipe provides 70 to 90% of the strength, this is how that variable or that variation in the number can occur. So type 1 would be a situation where you're probably relying on the pipe a little less, so like that 70%. And a type 4 would be where you're relying on your pipe more along the 90%. Type 3 is the most commonly specified and used in installations throughout the country. It is generally assumed to be applicable for most applications due to having a good soil envelope and pipe strength, modest soil quality, which is usually accessible, and modest compaction requirements. So it's likely type 3 will likely work on your job site. Okay, so we've talked a good bit about concrete pipe strength, but how do we actually test it? How do we prove that our pipe is going to meet the strength required? Back in the day, there are a few trials on how to test the strength of concrete pipe. Here's a fun picture of placing sandbags on the pipe to prove that it has this high strength that they were experiencing in the field. Current day pipe testing is completed using a 3-edge bearing test, also known as a deload test. This design procedure is described in ASTM C497. This test is a more conservative representation of the loads a pipe would experience in the field. Instead of having that full bedding and all the soil around it, we're simulating a worst case by point loading the pipe. So in a deload test, there's 2 different phases. The first is finding the actual deload, which is the load in pounds per linear foot per foot of diameter, applied to the point that the reinforcement is engaged and induces a 0.01 inch crack. The deload is considered the service load. Sometimes people get concerned when cracking occurs in concrete pipe. However, the mass majority of the time, the crack is not an issue. Why do you think it may not be an issue? Well, the reinforcement doesn't get activated until the concrete around it cracks. So when small cracks occur, it commonly just means that the system is working as intended. Now, the second phase of this testing that we do in our plants is called de-ultimate. This is where we test the pipe to the point where the reinforcement has yielded and the pipe can no longer accept additional load. If you haven't seen a 0.01 inch crack in real life, this picture is here just to give you a representation of what that crack might look like. All right, so ASTM C76 specification tells us the minimum deload and de-ultimate values needed to meet each of the 5 different pipe classes. Let's do an example. Say you have an 18-inch class 5 RCP in a 3-edge bearing test, or that deload test. For a class 5, the deload requirement is 3,000 pounds per foot. So 3,000 pounds times a standard 8-foot joint times 1.5 feet diameter would give you a total load capacity of 36,000 pounds. To solve for the de-ultimate load, you would insert 3,750 in for the 3,000, which is shown here on your de-ultimate chart. That means that the pipe could take up to 45,000 pounds before it reaches its ultimate load. In general, class 3 is the most commonly spec'd concrete pipe, which requires a minimum of 1,350 pounds per foot for your deload and 2,000 pounds per foot for your ultimate load. A great thing about concrete pipe is that the bigger the concrete pipe becomes, the more capacity the pipe must be able to resist. So let's compare a 12-inch and a 36-inch concrete pipe. A 12-inch D-load has a total of 16,000 pounds capacity, and a 36-inch D-load has a total of 48,000 pounds capacity. Therefore, 3 times the diameter is equal to 3 times the load capacity. And that is something that is very unique to rigid pipe structures and brings a great value into the job site. As you know, the bigger the structure, it's still going to be able to accept more load. Okay. Now that we all have a little bit of a background on how concrete pipe strengths are determined in the field and at the plant, how do you choose the correct one for your project? Well, there are 2 free options from the American Concrete Pipe Association that can assist you. That is the Pipe Pack software and the fill height tables. Now, the Pipe Pack software is efficient, but you do need to have a good understanding of the different design principles in order to get accurate results. The fill height tables are very quick, but you do need to understand the assumptions that are in the tables. So the ACPA fill height tables were completed using the indirect design method and in accordance to section 12.10.4.3 of AASHTO LRFD bridge design specs. I do find these tables personally are the easiest to use, but please be sure to double check all the notes and design assumptions and make sure that they align with what is specified and expected to be done on your project. Okay, let's walk through an example. I have chosen the fill height table that assumes a type 3 bedding, a soil weight of 120 pounds per cubic foot, and a positive projected embankment. If you are planning on using a 24-inch RCP, you can follow the chart to whatever fill height is applicable for your job. Now, moving through the chart, you can see that at 1 foot of fill, it requires a class 3 pipe. Once you move to 3 feet of fill, it actually starts to drop down a little bit, where you only need a class 2. And then for 4 and 5 and 6, you have your class 1 requirements. And then you start to see everything start to go back up. So as you hit 7 feet, you're back to a class 2, and 10 feet, you're back to a class 3. It is really rare for pipe manufacturers to make class 1 and class 2 concrete pipe. Typically, the lowest class produced is a class 3. So please keep that in mind. If you put a class 1 on your project, you're likely going to actually end up with a class 3. So just keep that in mind. But what that is telling us here on this screen is that a 24-inch pipe between 1 and 14 feet of fill, a class 3, is sufficient for design. Now, how often do you see drainage pipelines being installed deeper than 14 feet? It happens, but it's pretty uncommon. And that's why earlier I said class 3 is pretty common. It's the most common type of pipe. And this is a good example on why. Now, for those occasions where the fill heights are quite deep and do surpass the class 3 requirements, you can continue down the fill height table and see what classes are required. So in this scenario, up to 21 feet, a class 4 would work. And then up to 32 feet, a class 5 would work. After that, when you enter into this purple range, that is what is a special pipe design. So with the special pipe design, when that's needed, you should work with your local pipe manufacturer on what will be required to make that happen. It will be highly dependent on alternative reinforcing, potentially using stirrups throughout the pipe wall. And in some cases, we can actually increase the wall thickness in order to achieve more strength. but this is going to be highly dependent on our forming capabilities as well as our equipment. So if you run into one of those situations, please call us. Okay, another example I wanted to go over is an 18-inch pipe. So in general, it follows a very similar pattern as the 24-inch with one additional note. If you look here at the from 1 to 2 feet of fill, the class required is a class 4. Once you move to 2 feet of fill and up, your class drops back down to 1, 2, or 3, all the way up through 14 feet. This is a good example of why the fill height tables are extremely helpful for designers. You know what's going to be on your job site. You know what the trench is going to be, what installation type is supposed to be there. And so you can come into this chart and look and see where your project falls within this table. So if you have a substantial amount of your pipeline between 1 to 2 feet and you plan on using an 18-inch pipe, you should be putting on there that it's a class 4 pipe instead of a class 3. Okay, same sort of situation here with 18-inch. Once you pass the 14 feet, you would surpass the class 3 requirements and move on to class 4 and class 5. And then after 31 feet, you would find that special design. Okay, so let's talk a little bit about hydraulics. Now, hydraulics in itself could be a day-long seminar, so I'm not going to go into the details of how to calculate hydraulics, but I do want to talk about how we have different product lines that can help provide the same amount of hydraulic capacity for your job site and what tools are available for you to use to help assist. So on occasion, there is a need for alternative products to account for various project site limitations, economics of design, or really production timelines. We are going to go through an example using a free app, but you can always reach out to our sales team for assistance when determining the options you have. So the Compare Flow app can be found in your app store and installed on your tablet or your phone. Just look for the orange icon with the gray pipe. Once you open the app, there will be multiple concrete products to choose from. Based on your selections, you will be able to compare the flow capacities to different products. So let's run through an example. You have a project that needs a flow capacity of 140 cubic feet per second, and you plan on using reinforced concrete pipe. The standard option would be to supply a 72-inch concrete pipe. Taking into account the OD of the pipe and providing a minimum of 1 foot of cover over the pipe, you would need roughly 8 feet of depth. If that depth was not possible on your project and you wanted to stay within the pipe options that we offer, you could potentially drop down to an elliptical pipe. Elliptical pipes are exactly what they sound. They're just your round pipes with a little squished. This on the screen is a 72-inch equivalent elliptical pipe, and it would bring the depth needed on your job site down to roughly 6.5 feet. Now, if that still was too much, you could also utilize a triple run of 48-inch pipe, which would be at a minimum depth of just under 6 feet. Now, the 48-inch option, although it is the least amount of depth required, is going to require a very wide trench. The 3 pipe widths alone would add up to just under 15 feet, plus you would need some adequate space between the pipes to have proper compaction. So this is likely going to trigger some other issues on your job site where one is going to be very expensive to build because it's going to be a massive trench. And you could also potentially run into right-of-way issues or, run into other utilities that are within that area. So what else could you do? Well, You could also reach out and ask about concrete boxes. So here are two potential options that could work for the given project requirements. They both provide over 140 cubic feet per second of flow capacity, and they have a little bit different of configurations. So a 6 foot wide, 5 foot tall concrete box would be roughly 6.5 feet in total depth. And an 8 foot wide by 4 foot tall concrete box would be roughly 5.5 feet depth. So out of all of the options that have been presented in this example, the lowest fill depth you could achieve would be with the 8x4 concrete box. And this option would take up a fraction of the trench width when compared to the triple line of 48-inch pipe. So if you take nothing else out of this hydraulics conversation, it's we make a lot of different structure types that can meet the needs for your project. So I strongly encourage you to use the Compare Flow app to get a kind of a gut idea of what options might be available, and then call us or your local pipe manufacturer and discuss what the options available to you are. Depending on the location, the manufacturer's equipment, and the current backlog of projects, some products might be a better fit than others for your job. Okay, our last topic of the day is going to be discussing manhole sizing and the Northwest Pipe manhole sizing tool, which is available on our website for you to use. Let's first discuss some rules of thumb. First, NPCA recommends that there's a minimum of 6 inches of concrete above an opening in order to ensure reinforcement can be placed in the concrete above, increase the structural integrity of the overall structure, and reduce any cracking during shipping and handling. When 6 inches above the opening is not possible, it's recommended that you split the opening between 2 different pieces. This allows for the load to travel around the opening onto the bottom concrete piece. It's important to note that when splitting an opening, it's best to maintain at least 1/3 of the diameter in any one piece. Now, this does become a little bit tricky when there's not a riser between the base and the top. Openings can't encroach the top slab, and those that are close will require special top slab designs to make sure that we can span over that opening properly. So we usually see this issue in low flow areas where there's really just not that much depth and you need to move a certain amount of water within this low depth area. If you find yourself with that sort of a project, I strongly encourage you to place the flow line as low as possible in order to maintain concrete above the openings in your precast structures. Next, NPCA also recommends 6 inches of concrete between multiple openings. This again ensures there is enough concrete between the opening to properly distribute the loads and maintain the structural integrity of the manhole. Remember that picture from the beginning of the presentation? It now has a big red X through it. This is a great example of what we do not want to see. We want to see more of what's shown on the left, where you have 6 inches on the inside face of your manhole in between the 2 different pipe openings. For a manhole with 1 hole in the piece, the final opening size should not be larger than 75% of the internal diameter or the section height. So let's talk through an example here. You have a 48-inch internal diameter manhole section that is 5 feet tall. 75% of that 5 feet is 45 inches. 75% of 48 inches is 36 inches. So your max opening that you can put in this manhole, or your max opening size, is 36 inches. For a manhole that has multiple openings, you cannot take out more than 70% of the circumference with openings. So let's talk through a very similar example. We have our 48-inch manhole again. It has a circumference of 150 inches. If you have two openings that are 36 inches, we already know a 36-inch opening is okay based on the last rule of thumb. But what happens when you have two of them? Well, that gives you a total of 72 inches in openings. 72 divided by 150 is 48% of the circumference. Therefore, you're okay. There's no issues within this rule of thumb. Now, if you have three openings that are 36 inches, that gives you a total opening space of 108. 108 divided by the 150 is 72% of the circumference. Therefore, it would not be recommended that you put all of those pipelines into a 48-inch manhole. So this brings us to the manhole sizing tool, which can be found on the Northwest Pipe website by navigating to resources, then the manhole sizing calculator. Here's an example I did using the online tool. On the slide is a screenshot of the calculator. Before you begin using the calculator, you will need to know the pipe type, pipe size, and the angles of the pipes. The output of the calculator will give you an estimated manhole diameter and let you know if you need an alternative joint placement to accommodate having a minimum of 6 inches of concrete above the opening. Something to note is that at Geneva, and this might be the case for other manufacturers as well, but at Geneva, the outlet is always set at 0, and then all the other pipelines are labeled clockwise from there. In this example, I used a 27-inch reinforced concrete pipe with an invert elevation of 1 foot and an 18-inch RCP with an invert elevation at 2 feet, coming in at 90 degrees from the outlet. The calculator estimated the configuration would need a 60-inch manhole. Now, if I were to change the 18-inch RCP to come in at an angle of 45 degrees instead of 90 degrees, the calculator would adjust to show that you need a minimum of a 108-inch diameter manhole in order to maintain that 6 inches of concrete in between the openings. If you are ever in doubt about manhole sizing on your projects, I highly encourage you to check out the calculator to get a good estimate or to call our sales team for help. Getting the right manhole size from the beginning can help reduce budget changes and any potential delays on your project. Okay, I know we covered a bunch of information in a short period of time. We would like to set aside the remaining time to answer some questions from you all. If you haven't put your questions in the Q&A section, please do so now. Everyone attending the webinar is on mute, so we aren't able to answer any raised hands. But if you type in your questions into the Q&A, we'd be happy to answer as many as possible as we can. In the event we can't answer everything today, we will do our best to answer questions at a later date.
So there's the question in the Q&A, would it ever make sense to specify a class 1 or a class 2 pipe? On occasion, I would say. Our standard that we manufacture at Geneva is pretty much class 3. We don't do much of the 1 and 2. However, when you get to bigger diameters, say 72-inch and larger, if you have a large quantity, it can be a cost savings for you. If we wanted to look at that, we could. But typically, if you're just doing a few hundred feet and it's a smaller diameter, it's not as much. We would probably just supply a class 3 as opposed to changing our equipment over to do something different.
Let's see here. So, for example, 18-inch concrete pipe, how does class 3 differ from class 4? Is it the wall thickness or reinforcement or both? Great question. Typically, it is the reinforcement. So when you move between the different class sizes, you're beefing up the reinforcement within the pipe wall, which increases the cost just based on materials. In the event that you move into like a special design type pipe where you have extreme fill height depths, for example, I've in the past worked on a project where we had I think it was like a 60-inch pipe, 100 feet depth in the ground, right? If you're in one of those situations, you're going to max out what you can put in that standard wall thickness, and that's where we would start increasing the wall thickness to get a little bit more capacity in the pipe.
Another question, is there an updated clearances table for RCP and manholes combo boxes? I'm guessing this might be in response to some of our old engineering guidelines that Geneva's had for years and years. I don't know if that has been updated, but I do know those clearances are probably a little bit different than what we had originally put out maybe 15 years ago. It's been a minute. So that's something we probably need to look into. If you have a question on that specifically, reach out to us and we can look at pipe size, and depending on the configuration, whether it's a curb inlet style box or just an area drain style box or even a manhole, we can help with that. But I don't know that we have anything readily available at the moment.
Let's see, we have another question where it says, where are you measuring fill heights from when using the tables? So I would say the top of grade. So with concrete pipe, we ask for 1 foot of cover over that pipe. And for ellipticals, the tables actually start at 6 inches. So depending on which table or which product you're using. Concrete box can be all the way down to at grade. So you could drive directly over the concrete box. That's not necessarily recommended just from a practical aspect, because in precast concrete, it can get a little slippery when wet. So if you're in a situation where you need very little cover over a concrete box, at a minimum, we recommend paving over it. Hopefully that helps answer that question. So we have another question here. Can you add multiple inlet pipes to the manhole sizing calculator? Yes, you can. You can add 2 different pipes coming into a manhole within that calculator. You can also change what type of pipe you're using. So there's, concrete, there's plastic, there's steel, there's a couple different varieties within that calculator already built in. So if you're using a variety of products on the job, you'll be able to use the tool as well. Another question, can your precast structures accept pipes through the corner of the structure? So that's a really great question.
I respond to that saying typically we try to avoid that unless absolutely necessary.
Yeah, and that would be my response as well. We typically try to avoid it. There are parts of the country that going through a corner happens frequently, but within the, I've worked a lot within like the Texas, Colorado, Utah region. It's very rare to see that, and it's generally not recommended within that region.
Ashley, there's one on the manhole calculator since you've used it. It's basically just for manholes. The question is, does the manhole calculator work with cleanout boxes? An example of the angle of pipes coming into a box. We do have a PDF that you can calculate what that opening would need to be. We don't have a pre-designed tool for that I'm aware of for boxes.
I'm not aware of one, but that doesn't mean we can't develop something in the future. So thank you for bringing that up.
So another one from Andrew. Have you supplied pipe for large vehicle loads and shallow cover less than a foot or approximately a foot, such as for a haul road or articulated dump truck traffic with fully loaded weights upwards of 80 tons or more? I would say it's doable. We just need to have all the appropriate information so we can run the calculations on it.
Yes, absolutely. It will be dependent on the pipe size, and then having that alternative vehicle. So we do have some design software within the industry that allows us to do alternative loading, not just HL93 or your normal ash tow truck. So we would just need to have the vehicle, the heaviest vehicle configuration, have that information and the project, soil conditions and etc. And we could run that design to see what would be appropriate.
Yeah, I think we pretty much hit most of the Q&A questions. There's some that came in the chat that we didn't have time to review, so feel free to reach out to us afterwards if you still have questions.
All right. Well, thank you very much. Thanks, Ashley. Thanks, Cody. And thank you, everyone, for joining us.